Welcome to the Frosty Drew Observatory and Science Center Stargazing Nights Live streaming event. Tonight we are coming at you from all of our homes in Connecticut and Rhode Island. And we're doing this as a way to bring the cosmos to you during this time of somewhat uncertainty or just new conditions that we're not used to dealing with. Now, we are all stuck at home just like you guys are. And we are using whatever resources we have to do what we do at Frosty Drew, which is to bring space and bring the universe to you guys. Now, unfortunately, like last week, we're experiencing some inclement weather. I mean, this is New England, right? And in New England, it rains and it's cloudy, and we're really great at that, right? So as a result, we're not going to be able to show any live images from our telescopes tonight that we have set up. Instead, we're going to show you images that we've captured over this past week or images that we've captured over the last year or so at Frosty Drew and doing our own work as well. Now, on tonight's session, we have 4 Frosty Drew Astronomers and we have 2 Frosty Drew Sky Evangelists serving as moderators. Our astronomers tonight are myself, Scott McNeil. We also have Derek. We have Sean, and we have Gavin, who was not with us last week, who is joining us this week as well. Our moderators are Jessica and Lindsay. As you're looking at the YouTube live stream, you'll notice on the right-hand side of your view is a chat window. This is the place for you guys to get into discussions and to ask questions. Our moderators are watching the stream, they're watching the chat, and they will be sending your questions to us to be answered. Now, I'll note that we do have a slight bit of a delay from the point that we're actually talking to the time the broadcast gets to you guys. So please bear with that if your question gets presented after we've switched the object we're viewing. I also want to do a quick shout out to all the fabulous people that donated last week. Last week's session was very well received. It was the first time we did this, and we were all very nervous because we didn't know how it was going to play out. We had some hiccups, but overall, we feel it went well. And numerous individuals had donated to us. And I can't tell you how happy and just how that makes me feel, because at Frosty Drew, this is a tough time for us. We can't open due to the current situation. And we are an organization that relies on donations. And not being able to open and collect donations, it really puts us into a tough situation. And we are not going to close, but we're already stretched thin, and stretching thinner to get through this is a stressful situation. And thanks to you guys, that stress has been alleviated. So high fives to all you guys that did that. You guys were amazing. So at this point, we're going to turn the discussion over to our astronomer, Gavin Olson.
Hey, everybody. So I've got a collection of images tonight that they all center around the constellation Orion. And what I'm trying to illustrate tonight is something that when I first started astronomy, you see these beautiful pictures on the Astronomy Picture of the Day or the news, and you wonder, how big is that? Are we very zoomed in, or is this just a very dim object in the telescope to see? Why don't I see these beautiful things when I look up in the sky? So what I'm going to try and do is a few pictures tonight is put them in context of the constellation in which they reside, so you kind of get a picture of how large they are and how relatively bright they are to each other. Get the present button here. Okay. So you should now see kind of a somewhat fuzzy view here of the constellation Orion. You can see the familiar belt here and the bright star Betelgeuse up in the corner here. So the 3 objects I want to draw your attention to tonight are, we have the Great Nebula in Orion, Messier object number 42, which is down in the Sword of Orion. The Horsehead Nebula, which is comes right down here off one of the belt stars, and the Rosette Nebula, which is off to the left of Betelgeuse here. As you can see, these objects are pretty large in the sky, probably slightly smaller than the full moon is. But because they're quite dim, you can't really see them with the naked eye, and that's where magnification comes in. So here is the M42, Messier object number 42, the Great Nebula in Orion. This image, each color of this image was about a 5-minute long exposure. Just the camera sitting there with the shutter open to capture 3 different wavelengths of light out in the infrared range that have now been scaled back to red, green, and blue visible light for us to analyze the image with. This is an object you could see with a pair of binoculars. If you track down from the Orion's belt there down the sword, it will pop out with binoculars. With a small spotting scope, you can get a really good view there. And something like the Observatory at Frosty Drew, you can actually zoom way in and kind of pan around it and get a really interesting view. So that object, like I said, it's down here off the belt. So that red box there is approximately the view that we were seeing in the blown up image there.
Now, Gavin, is the Orion Nebula, that's visible to the naked eye as well, isn't it?
Oh yeah, you should. Yeah, even with the naked eye, you will see a fuzziness up there. If you got good eyesight in some dark skies, what looks like it might just be a bunch of stars is actually nebulosity. The next object that we have here is much more difficult to see with the naked eye. Is the Horsehead Nebula. This image was taken in what's called hydrogen alpha light, which is the molecular hydrogen out in the interstellar medium. When it's excited and then falls back to a ground state, there's different transitions that can happen. And these are classified. One of them is the hydrogen alpha transition, is indicative of certain types of cloud. That kind of helps us do some science here. If we see that particular wavelength strongly and not a different one, we can gain some information about what the hydrogen is doing out there. In this particular case, it does produce a very beautiful image as well. So we got the main construct. So this bright spot here is actually one of the belt stars in Orion. Scott can probably inform us with the common name of that star.
On attack.
There we go. The other object visible here is the Flame Nebula, and that's probably much easier to see with a pair of binoculars or a small telescope. It's much brighter in the visible range, whereas the Horsehead structure here appears very dimly red, if at all visible. That's where a camera that's sensitive to this light's able to pull that object out much better. If we go back to our map here, that's hanging directly down from the belt star here. Now, the third and final object I have here is the Rosette Nebula. This picture here is again taken with 3 different narrow frequencies of light. That hydrogen alpha transition, like we discussed before, is in green. What's called the oxygen 3 line is in blue, and there's in red is a sulfur 2 transition. So that's, you can kind of, it appears in this image as this golden color where it's the red layered on top of the green. And like I said before, there's some structure here where the stellar phenomena that created this nebula, the gases are kind of stratified out and they're doing different things. So we can gain some insight as to what's going on by where we see different types of gas through that emission. So like I said, this object is off the top left of Orion here, and is similar in size to the Great Orion Nebula there, but somewhat dimmer. In the large image here, you can kind of see the relative brightness between these objects. So where M42 here is almost blown out, the other 2 objects are quite dim. In comparison with over to the right here is Westerly. Is another one of our things that we see in the sky, unfortunately, in Frosty Drew. I don't know if Scott has any more commentary here on the lore or science of these objects. Otherwise, I can pass it on.
First, what Gavin was mentioning when he said westerly is light pollution. So at Frosty Drew, though we are one of the darkest spots in southern New England, we do have a lot of light pollution from some of the surrounding communities. And towards our western horizon or our western sky, we do get some light spill, which is artificial light that is visible in the sky from the surrounding communities. In this case, Westerly and some of those, New London, some other communities in Connecticut. And that does give us this is a good example of one of the reasons why light pollution is pretty rough to deal with, because it really floods the sky with light and makes it difficult for us to see everything else. As for the objects that Gavin is showing you, this is an excellent showcase of what is visible just beyond your sight when you're looking at the sky. Now, the darker your location, the less light pollution you have to deal with, the better you'll be able to see some of these features. The Orion Nebula, for example, it's one of 2 naked eye visible star-forming nebulae. The Orion Nebula is the center star in the Sword of Orion, which is the perpendicular line of stars to Orion's belt just underneath. It looks like a star to the naked eye, but if you get dark enough skies, like Gavin was saying, it starts to look really blurry or fuzzy. And you start noticing that it doesn't really look like a star. It definitely has a very conspicuous nature to it. The Rosette Nebula as well, that's another object that becomes quite visible under dark skies. Now, most of these objects are all working together. They're part of what we call the Orion Molecular Cloud Complex. And it is a humongous region that's in the constellation Orion of star formation, hydrogen ionization, all kinds of really great features. And you'll notice that around the constellation Orion on the screen right here, you have that arc of nebula. That's called Barnard's Loop. And Barnard's Loop is a large supernova remnant. When you look at the star Betelgeuse, which is the brightest star on the screen right now, Betelgeuse is a rogue star. It is a star that was part of at least a binary system, at least 2 stars, where the other star ended up as a supernova and it ejected Betelgeuse. And for a while, we thought it possibly could have came from the same supernovae that created Barnard's Loop, though with newer data, we realized that it did not.
So Scott, Charlene Tuttle had a question. She said, what keeps the gases so separate? Density or fluid layering or plasma?
So what happens is these gases are products of a specific process. So it's not that they're being separated from each other by something along the interstellar medium or something that's just in space. What's happening is in the areas where you have star formation, like the Orion Nebula, places like the Flame Nebula, places like the Rosette Nebula, what's happening is you have a molecular hydrogen cloud or a nebula. And inside that nebula, something has disturbed it. And that disturbance has caused little dents or little points in space-time, which that's gravity. And that gravity started pulling in a lot of the mass in that cloud, which is a hydrogen gas cloud, the nebula itself. And eventually stars started forming. And that's why that nebula is visible in that area. Barnard's Loop, for example, being a supernova remnant, it is the outer shell of a high mass star that was blown off the star's core when the star died. And it continues to expand outward. The reason why it's visible is because there is bright stars nearby that are emitting a lot of ultraviolet radiation, and it's ionizing the gas in the cloud, causing it to glow a little bit, and we can see that.
Jean Benjamin asks, would Hubble photos look the way in real life if one were close enough?
So does anyone else want to take that? Gavin? I know you work with the Hubble palette, don't you?
Yeah. So what I mentioned earlier, where I was mapping, these different infrared wavelengths into the different color channels of my image. The term for that particular mapping of hydrogen alpha to green and sulfur 2 to red and so forth is called the Hubble palette. And it's so named because the particular instruments that are on the Hubble Space Telescope also image in these wavelengths. And when the scientists are producing images, they're for the public that are in these in a false color, they use a consistent way of rendering them, which we kind of, as amateur astronomers, kind of emulate with our pictures. So a lot of the color that you see in those Hubble Space Telescope images is a false color, and it's non-visible light that has been shifted down into the visible range.
It's also important to note that though with Hubble, as Gavin's saying, they're mapping wavelengths of light that we don't typically see to colors that our eyes understand, these objects are very big. We're talking like the Orion Nebula. The Orion Nebula is about 25 light years in diameter. I mean, that's large. I mean, you're talking one light year is 5.9 trillion miles. So if you're closer to these objects, they're still very large in the sky. If you get close enough, you're not even going to notice it. But additionally, when we capture these different wavelengths of light like Hubble does, we collect a very significant amount of light that is visible in the molecular cloud while blocking a lot of the other light that's coming out, like starlight, light that is not interacting with the nebula, light that's not part of ionization. This is just broad spectrum light. And by blocking that, it allows us to bring out more detail in the nebula. And that's very, very much like it works with Hubble. So if you were actually faced with an object like this, you wouldn't see it exactly the same as Hubble sees it for the reasons Gavin described, but also the stars would be much brighter. Specific regions of it would be way brighter than the other parts that are much dimmer, because you would be seeing the broad spectrum light in the visible spectrum, which you wouldn't be seeing in the images.
We had one other question here from Oscar Quinn, who is 7 years old. He says, how are meteors made? And do you have any pictures of them?
Meteors. So that's a really great question. And it's a perfect time for that question too, because this coming Wednesday, we have the Lyrid meteor shower happening. It's the Lyrid meteor shower peak. Now, this is an important meteor shower, and not because it produces a lot of meteors, but because this is the first meteor shower that ends a very long lull or a low period of meteor activity that starts in early January and continues until April 22nd. During that time period, we have no notable meteor showers that occur. The Lyrids is the first notable meteor shower. Now, the meteors they're pretty much leftover material from comets that pass through the solar system. They come into the solar system, they go around the sun, and then they come back out. And behind them, they leave a little bit of a debris field, little pieces. So we're talking dust-sized pieces. Some of them are rice grain-sized pieces. Tiny pieces of comet get left in the debris field behind a comet. And then when Earth orbits through that debris field, Earth's gravity captures those little particles. And as they enter Earth's atmosphere and start encountering the mass and the density of Earth's atmosphere, they start to heat up and they burn up. And we see them as streaks across the sky. As far as pictures of meteors, yeah, we got some. Does any of you guys have a picture you guys want to show, or am I going to throw up a picture? I'll take it that I'm going to throw up a picture. How's that?
I think it might be up to you. I've actually been wildly unsuccessful in getting meteors with my camera. I have seen many an excellent meteor at Frosty Drew, but unfortunately my camera has missed them all.
When you're at Frosty Drew, any given night, even outside of a meteor shower, you can see up to 5 meteors per night. And sometimes we see quite a bit more than that. So here is a picture that I took in 2015 of the Perseid meteor shower at Frosty Drew Observatory. Give me 1 second here, and I'll throw it up on the screen for you.
I've got one to follow that, Scott.
Excellent. Yeah. I mean, I'm all about people requesting images, so if you want some requests, send them up. All right, here we go. This is the Perseid meteor shower of 2015. We captured this over a period of about 3 nights. When you look at this image here, there are a lot of meteors in view. You also notice that right about here you have the Andromeda Galaxy. Right
nice.
here you have the Perseus double cluster, and this light you see in the middle right here, this is the Milky Way that we're looking at. Now, if you follow all of these meteors back to the point of origin, or it looks like where they're coming from, it brings you right about to this star over in here. And this star is called Miram, and it's in the constellation Perseus. And Miram is the radiant point of the Perseid meteor shower. Now, the radiant point is where all meteors appear to originate from in the sky, and that's how a meteor shower gets its name. This is the Perseid meteor shower because the meteors radiate from the constellation Perseus. The Lyrid meteor shower, which happens on Wednesday, all the meteors appear to radiate from the constellation Lyra. A good way to find Lyra is to find one of the brightest stars you see in the night sky. It's called Vega, and about 8 degrees to the west of Vega is the radiant point of the Lyrid meteor shower. Though a quick addendum to that, to today's standards, it's actually not Lyra anymore. It's actually the constellation Hercules where the radiant point is. Though the names of the meteor showers predate the actual official boundaries that were established by the International Astronomy Union sometime in maybe 1940s. But the Lyrids continue to keep their name to this day. So this is an image of the Perseus. I'm going to relinquish my desktop now so Derek can show his image of meteor awesomeness.
All right, so this is actually an animation of a single meteor that I caught a couple of years ago. And let's see, I'm sorry, technical difficulties. Let's see. Apparently it wants to be on the same window. Yes. All right. There we go. All right. So this hopefully will be, it'll be an animation in a loop, and you should be able to see the Perseid meteor kind of in the upper right corner. And it doesn't look like it's looping anymore.
Is it that persistent train that's there? Is that what I'm looking at?
So you'll see the little trail there, but it's supposed to be in a loop. And you see the actual meteor, and then you get 3 or 4 images where it you can see how the smoke trail changes over time. I don't know why that's not looping now.
It doesn't like you.
It doesn't like me. Yeah.
It's like the weather.
It's like the weather. All right. Well, we'll go with that for a second and see if oh, come on. Sorry, this is all fun. I'm doing this for the first time. Because the other thing that's interesting in that image, is, to me at least, is there is you can see the Perseid, you can see the Pleiades as well as part of the Taurus, the bull. Let's see if we can do this real quick. Sorry, bear with me. Let's try it from maybe. Hey, there we go. All right. So you'll see the first frame, which is the bright meteor streak, and then you can see how the smoke trail changes over the next several frames. Just to kind of give you an idea of like what the meteor like actually leaves material in the atmosphere over its distance, and then the atmospheric winds move that material around, and in this case kind of tied it into a knot, and then it dissipated. So I thought that was really cool. Caught that a couple years ago during the Perseids, the same meteor shower that Scott was showing us. So
that is
all right.
pretty wild. That's awesome.
Yeah.
That was a fabulous night. The Perseid meteor shower at Frosty Drew and largely for New England happens in August. And August is wildfire season. And though we don't get wildfires in New England, we get the wildfire smoke. And that's why you get those really amazing sunsets and sunrises with a big red sun and the red moon when the moon rises. But as a result, we missed out on the Perseids quite frequently. That year was just fabulous. And at Frosty Drew, we call it the anti-sleepathon because we usually run the event for 3 nights. We're out all night long, running the events, doing the data collection, and then all day we're processing the data sets and getting them out to the media just to get back out the next night. By the time we get to like the third night, we don't even know what we're talking about anymore.
Yeah.
We good for questions, guys? All right,
Yep,
so
we
are we good for Sean to step up?
Sure. Hold on one sec. Let me pick up a picture. All right. Hi, everyone. I'm Sean. I'm one of the astronomers. I've been with Frosty Drew for a few years now. I also do astrophotography, much like most of our astronomers on the team. So I got a few images I want to share of the things that I've captured over the years. And I'm going to start with something called the California Nebula. Give me one sec. I'm sharing the wrong one. All right. Everyone can see it?
Yep.
All right. So this is the top half of the California Nebula. This is shot in hydrogen alpha. Also, Gavin explained that earlier. Just narrowband wavelength. The others, popular ones being oxygen 2 and oxygen 3 and sulfur 2. So this is just the top half of the California Nebula, and it's so named because it looks like the state of California. And you can kind of see how this would be the upper structure of California. This is an enormous nebula. I don't have a good scale image like Gavin was showing, but this is only the top half, and to complete the image, I would need at least 3 of these images stacked on top of each other, give good margins. It's just an absolutely enormous image. It's an emission nebula, which means it emits those wavelengths of light that Gavin and Scott were talking about earlier, and which is why I can capture it in hydrogen alpha with this filter. Scott, do you have anything more sciencey to add to this?
So, like Sean was saying, this object it's very similar in wavelengths to what we're looking at with the Orion Nebula or the Horsehead Nebula or the Flame Nebula. And it's because you're looking at ionized hydrogen. Again, this is a hydrogen gas cloud in space, a nebula. And a nearby star is casting a substantial amount of ultraviolet radiation into this nebula, which ionizes it. And that ionization process isn't what makes it glow. What happens is when an atom is ionized, when the electron is blown off the atom, and you're left with a negatively charged atom. It's called an ion. But these electrons and these ions, they want to reconnect. When they reconnect, they get excited. And as they return to a restful state or a ground state, they release a little bit of energy in the form of a photon, and that's what causes it to glow. And we can see that. Now, this object is 1,000 light years distant from us, and it spans an area of almost 80 light years. Like, as Sean was saying, this object is huge. And it's just beyond the visible or naked eye visibility in the sky, and largely because it's ionized hydrogen, so it's red to our eyes. If this was blue, for example, we would probably be able to see it under dark enough skies just by looking up.
Scott, someone had a question here, or Sean, whoever wants to answer it. Now, I am not an astronomer, so I might be saying this wrong, but he says, is it possible to see the large Magellanic around here? And then do you have any pictures?
So, Sean, you want to answer that?
Sure, that's a negative. The large and small Magellanic Clouds are southern hemisphere objects. So I do not have any pictures. I have never been to the southern hemisphere. I don't know about you guys. Nothing.
No.
Nothing. No pics.
No. So, Gavin?
No. We get a pole star, they get all the really cool big objects.
Yeah. Yeah, so that's the answer to that.
All right, so Michaela, I hope that answers your question. And then we had another kind of question from Ken. Said Ken and Leaf would like to hear the story of Frosty Drew and why the observatory is named for him.
Okay, I'll take that. So that's an excellent question, and it's actually something we probably should be covering every time we do this. So Frosty Drew, we were all hanging out one night and we were really getting loaded drinking, and we said, why don't we create something called the Frosty Brew, and it just happened. No, I'm kidding. So Frosty Drew. Frosty Drew is our namesake. It's named after an individual whose name was Edwin Foster Drew. His nickname was Frosty. And Edwin Drew, when he was young, he contracted polio. And though he survived the disease itself, it left him quite disabled. Though Edwin Drew had a fantastic way of speaking to the public and maybe helping people see things that they wouldn't have readily seen on their own. He was a fantastic individual. He was very connected with nature and ecology, and he was very active in the community. So Ninigret Park, which is home to Frosty Drew Observatory, used to be the Navy's auxiliary landing field. And in the early 70s, the Navy had decommissioned it. During World War II, it was very highly used. There were some famous pilots that had gone through that landing field, including George H.W. Bush. Though once it was decommissioned, the land went up to the highest bidder. And it was right around that time that the rules changed regarding old military-based land relinquishment. Initially, it would be given to communities and states as parkland or national wildlife refuge land, things like that. Though they changed the rules that whoever bids the highest can get it. And at the time, it was a nuclear power plant that was bidding on the land. Edwin Drew put together a petition which turned into a coalition or a lobbying group to have that Navy auxiliary landing field land turned over to the town of Charlestown as parkland, and another part of it turned over to the Department of the Interior as a national wildlife refuge. And they succeeded in this. And that's why we have the park we have today. That's part of it. That was the start of it. I mean, there was a lot of people that were involved in making that place as awesome as it is. But Edwin Drew got it started. Now, shortly after this, Frosty Drew ended up dying largely from his complications that he had experienced from polio. And they opened the Frosty Drew Memorial Fund, which was the Frosty Drew Nature Center, as a living memorial to Edwin Foster Drew. In 1986, during a meeting at the Nature Center, they realized how amazing the skies were and how wide open everything was. And they decided that it was time to open up an observatory. And that puts us where we are today. And that is the story in a nutshell of Edwin Drew. Though, let me just put this out there. Edwin Drew was an amazing person, but he wasn't such a saint that a lot of people kind of think of him as. Edwin Drew was a rocker. Word on the street is he used to drive around town in a spacesuit. And he got busted a few times doing some rather illicit activities. He was an underdog. And every time we do something that I feel doesn't fully align with the larger physics community or is something that a lot of people may consider radical, I feel like we're living up to the expectations of Frosty Drew.
Nice. Thank you, Scott.
All right, ready for the next one?
Absolutely.
Do it.
All right. So here's my next image, which is the Crescent Nebula. This one can be found in the constellation Cygnus, Cygnus the Swan. I don't have a wide-scale image of that to show everyone, but if you guys stop by during the next time we actually can get to the observatory, I'll go on to show you guys Cygnus the Swan. So this one's a really cool object. This one I shot in bicolor narrowband. So all the red you see is the hydrogen alpha wavelength, which we've covered in quite detail now tonight. And then there's another color in here that it's kind of, you can't really see a whole lot of it, but you can see a blue halo around this star. So it's the oxygen 3 spectrum. There should be a faint veil of blue riding the top of this, the Crescent Nebula, which is the oxygen. However, I wasn't able to get that to come out quite as good. And there's a lot of hydrogen alpha in this object, so it's way easy to overdo that. I've always thought this object is cool because it kind of looks like a brain, if you can imagine the ripples in the brain structure. This is excited by a Wolf-Rayet star, correct, Scott?
Oh, yeah.
Yeah, so if you want, you could probably go into a little more detail on that than I can.
So look at this image. This is one of the fabulous things about a Wolf-Rayet star. So when you're looking at this image, you're going to see, you see that almost like the waves moving through this nebula. So this is a product of a Wolf-Rayet star. So a Wolf-Rayet star is a very old star that has already entered the red giant stage. Though a Wolf-Rayet star is very high mass and it puts out a substantial amount of stellar winds. So when you think of stellar winds, it's kind of like the solar wind with the sun. You have this constant outflow of energy. In this case, it's charged particles, plasma, and they're magnetized. And they move through the solar system. They deflect a lot of cosmic rays and gamma radiation from space. And everything inside that solar wind is considered the heliosphere. Now, in the case of a Wolf-Rayet star, when the star goes into the red giant stage, the stellar winds that come out of the star are moving kind of slow. But the Wolf-Rayet star, once it gets later in that stage, once it gets older, those stellar winds start to increase. And eventually, the stellar winds coming out of the Wolf-Rayet star catch up to the stellar winds that it emit when it went into its red giant stage, which are moving much slower. And they start to interact and they ionize each other. That's what you're seeing right here. And this is an excellent example of a Wolf-Rayet star. I mean, some basic numbers here. This is about 5,000 light years distant from us in the constellation Cygnus. And Sean's image is a fantastic representation of this object, including all of that nebulosity you see in the background, which is generally considered what we call IFN, or interstellar flux nebula. Most of it is cold hydrogen. It just exists in the galaxy along what we would consider the interstellar medium, which is the space in between stars. Though when it gets near stars that have enough ultraviolet radiation, it'll ionize that gas.
I think there's a couple of questions. Lindsay, did you want to give one? Well, one that GMAC, a question that GMAC had, he is a 6th grader joining us tonight. He says, how long does it take for light to reach us?
That is an excellent question. So you have to look at light. And you know, the way you phrased it is really good too. Because a lot of people kind of, when they look at things, they think that you're reaching out and catching the light. But that's not the case. The light is coming to you. You only see photons that enter your eye and interact with the photoreceptors on your retina. So when we look into space, everywhere we look, even here on Earth, we see light moving at the speed of light. The speed of light is a static speed. It doesn't slow down. It doesn't speed up. And the speed of light is 186,000 miles per second. Now, when we look here on Earth, we pretty much don't notice the speed of light because it happens so quickly. Everything looks to us like it's in real time. But when we start looking into space is where those huge distances start to become a problem. So in space, instead of measuring things in miles like we do here on Earth, we measure distances in light years. It's one of the measurements we use. And 1 light year is equal to 5.9 trillion miles. And it is the distance that it takes light to travel at the speed of light over the course of 1 year. So when we're looking at this object that Sean has on the screen here, the Crescent Nebula, this Wolf-Rayet star, this object is 1,000 light years away from us. So that means it took 1,000 years for that light to reach our eyes. And when you look at this in a telescope, or when Sean captured this image, that light had been traveling for 1,000 years before his camera picked it up or before your eyes would see it. The objects we look at, they look the way they did when the light left. So when you're looking at these 1,000-year-old photons of light that are traveling towards, these little pieces of energy, your view is 1,000 years in the past. And that can give you an example of how much space is out there.
Hey, Scott. Quick question. Don wants to know what the status of Comet Atlas is, whether it's breaking up or getting stronger.
Comet Atlas is a hoax. Don't believe it. No, I'm kidding.
Hear that, Don?
I'm kidding. I see Lindsay down, and Lindsay's like, "Oh no, I put a hoax question up." So, Comet Atlas. So when it gets to be my turn to present, I'm going to put up some images of Comet Atlas. So yes, unfortunately, we mentioned it last week during the live stream that Comet Atlas was becoming a really fabulous comet, and that we had a good month and a half left of viewing where it would continue to brighten. Though I did put out there the addendum or the disclaimer that Comet Atlas may have fractured, and if so, it may be breaking apart before it reaches perihelion. At this point, that appears to be what's happening. Comet Atlas has fractured, and at this point, it appears that there are two nucleuses involved in a comet, and that's because the comet has not only split in half, it is split into multiple pieces with two very large pieces remaining. Though it is dimmed by a factor of 6.5 since last week. And that tells us that all of the volatile materials that are in that comet, all the dust, all of the materials that can turn gaseous and form into that bright comet, that atmosphere around the comet, have been expended and exhausted. And as a result, the comet is getting dimmer and dimmer and will probably not survive up to the point that it reaches perihelion. So I would have to say that Comet Atlas has died, unfortunately. And considering this comet has a 6,000-year orbital period, it's kind of sad. I mean, it's been hanging out, living for all this time, good old life, and then it got kind of pushed in from the Oort cloud from a CME from maybe Sirius or Alpha Centauri, and now it came in and encountered a stellar wind, and now it's dead. So thanks a lot. But regardless, Comet Atlas is definitely breaking apart, and I don't think we're going to see it become the fabulous naked eye comet that we hope. Though when I talk later, there is another comet that may become the rebound comet, and I'll mention it then.
Sean, I think there's a question here for you from Marie. She said, what kind of cameras and filters do you use? What is important to know about the photography of stars?
There's a lot involved. So I'll start with the first part, the camera. I have a dedicated astrophotography camera. I don't have it around me, so I can't go grab it to show you guys. But most of us use ZWO brand cameras, which are astronomy dedicated cameras. So they come in color or black and white, but they don't look anything like you would think a camera does. They're basically a cylinder and a sensor and maybe a cooler that's inside of it to keep the sensor nice and cool. But the camera I use is a black and white camera. It is a CMOS type sensor, and it's extremely sensitive to very faint light, which helps gather these objects we're trying to look at, the very weak photons that we have been traveling for thousands of years to get to us. So a lot of the images I show you that are black and white, I have filters in front of them. They just appear black and white because they don't exist with any other data. So the filters I use are mostly narrowband filters. I don't know if you were tuning in earlier, but we talked about how there are three main types of narrowband filters that we use: hydrogen alpha, oxygen 3, and sulfur 2. And those filters isolate the specific wavelengths for the hydrogen alpha line in the spectrum or oxygen 3 line in the spectrum. Scott can get into more of the sciencey details behind that, but it's basically an emission line that we're looking for. Now you can do DSLR photography. That's how I got into it. I have a Canon 40D that I have been using for many years. And I have an image that I'll show you guys that I took with the Canon 40D on a tripod. Some of the most important parts with photography in astrophotography is you got to have a firm tripod or a good mount. I've gone through 3 mounts now before finally getting a tank of a mount that can hold 110 pounds. Because you're looking at an object that's it could be very large in the sky, but you're zooming into narrowing your field of view into a very small area in the sky, and you have to track that area and expose for minutes at a time. So you don't want blurry stars or oblong stars, and you have to account for wind and the weight of your mount and tripod and everything. So you want to make sure that you have a good firm mount. And I say that to everyone who asks about astrophotography. Most important thing is the mount.
So no one ever seems to believe that.
No, not even me. Even when I read it, I didn't believe that.
You know, I think everyone has made that mistake. We tell people, don't spend your money on the telescope, spend your money on the mount. Because if you have a fabulous telescope and an amazing camera and a terrible mount, your images are junk. But nobody listens. I didn't listen. Sean didn't listen.
Yep.
And we all went through those learning curves.
Yeah.
And it's just because you got to change your thinking. But John is right. There's a lot involved in astrophotography. Though you can start very easily with just getting a tripod and like your DSLR camera. This right here, this is a Canon 60D. And I use this for an immense amount of astrophotography. This here is the new Canon RA. This camera is amazing at astrophotography, but it is a bit expensive. But if you take your camera, stick it on a tripod, and try to get some pictures of the moon. Once you get really good at imaging the moon, move on. And what's going to happen is you're going to graduate slowly to the more advanced levels instead of jumping the gun and finding yourself in an area where you just don't fully understand what you're doing and you're frustrated. So let's do this. Derek, you want to take over?
Yeah, I can do a couple images, I think. Let's see. We'll start. All right. Can you knock Sean off from presenting?
Yeah. You could just hit his thing and just
no, I got it. Yeah. All right. So we're going to start with a picture that I took last year of the lunar eclipse that happened in January. This is a composite image that I took that night, and it represents 3 stages of the eclipse. And it goes from right to left. Earth's shadow moves across the face of the moon, and you can kind of see that in the rightmost image that the Earth's shadow is obstructing about a little over half of the illuminated part of the moon. The middle image is where the moon is in the full shadow of the Earth, and you can see at the top of the image that the moon is a little bit brighter and the bottom of the image is a little bit darker, and that's because the moon didn't go through the center of the shadow. It kind of went through the Earth's shadow such that the top of the moon would be closer to the area that isn't a shadow, and the bottom of the moon is deeper into that shadow. And then the left image is, after the moon has started coming from behind the shadow and, seeing direct sunlight again. And the red color comes from the light that is refracting through Earth's atmosphere, hitting the moon. So that's kind of interesting to me that we're seeing Earth's atmosphere, the color that Earth's atmosphere puts on light as that light passes through the atmosphere before hitting the moon and bouncing back to us and being captured by a camera. I don't know if anybody had to jump in. Any more factoids about lunar eclipses that I might have missed?
These are fabulous images, Derek. This eclipse was just an amazing event. And I'm going to note something about this. So this happened when we had a crazy snowstorm and then an ice storm, and we didn't know what was going on. We had an event planned and we had to cancel it because we didn't know how safe the roads were. So I was sitting at home and I'm chatting with some of my weather friends on Twitter, and I'm like, what's the conditions? I hear that it's a disaster out there, but is it really that bad? And I'm hearing that there are accidents, but I also hear the roads are clear. So I'm like, you know what? I'm going to drive out of my cul-de-sac, which attached to a cul-de-sac, and I'm going to brave the ice. I'm going to try to get down the Frosty Drew. But once I got out of the cul-de-sacs, the roads were fine. I went down the Frosty Drew, and the skies were crystal clear. We set up our cameras, and that eclipse blew my mind. Though it was negative 20-degree wind chills that night. It was so cold that the cables on my mount broke, and they started arcing. And I was losing my tracking, and I couldn't figure out why. And I take a look, and I see sparks down by the plug. That's how cold it was. I lost my voice for 2 weeks after that night, but it was an unbelievable eclipse.
The battery on my camera froze, and I had to put it in my pocket in between images to keep the battery warm enough to take the image of the moon every 5 minutes.
So for the person who asked about imaging a moment ago, listen to all this.
Yeah.
And I'm sure that a lot of our closely followed friends that are into night photography, people like, again, another shout out here to James Iverson Crouch, can tell you that if you want to get that amazing, fabulous image, you have to suffer.
Yeah, you got to put in that time.
Oh, yeah.
You got to sit out there and struggle with your mount and struggle with the cables and just everything. Everything.
You'll spend more time setting up than actually doing astrophotography.
Oh, yeah.
Yeah.
And swearing.
Oh, yeah.
Yeah.
So the next image I have is a single shot of the Pleiades taken with a color camera on a 1,000 millimeter Newtonian telescope on a tracking mount. This is probably an image that was, a minute, maybe 2 minutes long. And you can start to see like there's a faint glow around all of these stars. And this isn't apparent when you look at the Pleiades through a telescope because it is extremely faint. The Pleiades are the gases there are what's known as a reflection nebula. And this is a little bit different than what we were talking about earlier with the nebulas that we were showing, where those were emission nebulas. So this nebula is actually the starlight reflecting off of the dust instead of the dust itself emitting light in different wavelengths. And the next picture I have here is the processed version of this, where about 10 images were stacked together and then processed to bring out more detail in that nebula, and then the background was corrected for black. So you can kind of see that, there's a lot of detail here around that reflection nebula, and the stars are, these spikes around the stars are actually an artifact of the telescope. That is if you're not familiar with the front end of a Newtonian telescope, there's something up there called the spider, and that is holding the secondary mirror, and the spider causes diffraction in the light, and we see that as diffraction spikes around the stars. I saw something pop up, maybe a question there. Okay. All right. So the next picture that I have is an open star cluster. It's called the Owl Nebula, the Owl Cluster. This is in Cassiopeia. And you can see there's two bright stars that kind of form eyes, and then these stars off to the left and off to the right, and then down here to make 2 feet, kind of make an owl formation. And this cluster is roughly 8,000 light years away in the constellation of Cassiopeia, which, if you're familiar with the constellations, or not familiar with them, that's kind of a W formation. that's near the Big Dipper or across from the Big Dipper. So going kind of quick. So the next one I have is another single shot image of a Messier object, and it's been a little bit processed to try to bring out some detail. This one is the second dimmest Messier object. This is M74, which is also called the Phantom Galaxy. M101 is the dimmest Messier object. And you can see this is a spiral galaxy. You can see the spiral arms, and then these blue regions in here are kind of active star-forming regions where, similar to what we saw with the Orion Nebula, there are new stars being formed there, and that's the gases along the galaxy arms that are grouped together more closely.
That's probably the most symmetric face-on galaxy I've seen.
Yeah, this is a really good one. M101 has got a pretty good face-on spiral as well, but that one is even dimmer than this one, so it takes a lot more time. And just to kind of give some notes on people for astrophotography, you can kind of see this red glow around the edge of my image here. And that's called amp glow, and that's an artifact of the sensor on the camera when the data gets read out of the camera.
How big of a field of view is this?
This is about half the width of the moon. So edge to edge, the full moon would fit in here about half.
Yeah.
Whereas in the Pleiades image, the field of view here is about the same as a full moon. So,
Cool. Derek, there was a question here about the Cassiopeia one. It said,
okay.
Where is the owl in the W of Cassiopeia?
So if you draw a line, so if you there's two. Sorry, I'm gonna try to do this. I don't have a picture of Cassiopeia to show you. But if the two sides of Cassiopeia, you have the deeper V and the shallower V. If you draw a line down the deeper V, the right side of it, and continue down for a little ways, maybe if you hold your hands at your arm's length, it's like 2.5 hands down, and it lands about right there. So it's below the W in Cassiopeia, or above the W, depending on where Cassiopeia is in the sky. So if it's an M, it's above the M. If it's a W, it's below the W.
That makes sense.
Now, what Derek's working through there, it's called a process we called star hopping, where so you look up in your star chart, there's this owl cluster that's something interesting you want to look at, but it's not something you can see naked eye. So say you're with your binoculars trying to find the object, you can see the stars in Cassiopeia, so you'd say, okay, I'm going to start at this star, and then I know there's a slightly dimmer star in this direction. I'm going to get to that one. And then I've got a slightly dimmer thing in this next direction, and I find that one. And eventually you can get to the object that you found in your star chart that you couldn't have just looked up in the sky to see. And that's another good skill you can develop without a lot of equipment.
Yes, pair of binoculars is the best thing you can really learn to star hop with, because they have a nice wide field, and they're very forgiving when you take a wrong turn.
Not only that, you can see just about anything you want to see or you're going to see with binoculars. I'd argue even more because of the field of view.
Yeah.
Hey guys, Marie had a question. She wanted to know what is happening with, probably going to pronounce it wrong, but Betelgeuse or Betelgeuse. How do you pronounce it again?
However,
there's a lot of different pronunciations for that star. It's commonly referred to as Betelgeuse, but sometimes you can call it Betelgeuse or Betelgeuse or Betelgeuse.
Right.
So, anyone want to take that, or you want me to take it?
I'll
take it. So, what's happening with Betelgeuse? So Betelgeuse is a really interesting star. When we think about all the stars in the sky, and this comes back to the question we had earlier about light years and distance, You know, we see a lot of these stars, but we're not seeing them as they look today. We're seeing them as they look when the light, it gets here. Betelgeuse is between 600 and 800 light years, with about 724 light years distant being a pretty good marker. So it takes about 724 years for the light from Betelgeuse to get here. But Betelgeuse is a very high mass star. I think it's in the top 12 most massive stars we know of. And at that point, Betelgeuse is very far in its life. It is well into the red giant stage, and it is getting very close to the end of its life. Now, that star, being that high mass and that close to the end of its life, will be a supernova. So another way to look at it, too, is that it may be the only ghost we actually see in the sky. You know, all those stars we see in the sky, most of those stars, even though we're seeing the light in the past, they're still there. That distance and that time period isn't that big compared to the lifespan of these stars. Though Betelgeuse being so close to the end of its life, it may have already gone supernova, and we're just seeing that old starlight waiting for the supernova to get here. Over the last 6 months, we witnessed a very significant dimming. It's called fainting in the amount of light that Betelgeuse was putting out. And it became quite dim compared to the stars around it. Now, Betelgeuse is a variable star, and that variability means that the star it's different brightnesses at different times, and it has a charted period of brightening and dimming, though we never seen it get this dim. And because it's a star that has a lot of hype around the possibility of it going supernovae, which would be amazing to see in the sky, this dimming raised a lot of questions, and it really got a lot of people excited about the possibility of it becoming a supernova. Though a star that could go supernova may dim before it goes supernova, I don't think we would see a slow dimming over a period of 6 months or 3 months. We would see a dimming over a period of maybe a couple weeks. So there's no star that has gone supernova that's been cataloged that has gone through such a dimming. So it doesn't necessarily mean that we were experiencing a supernova about to happen. What it likely meant is that we were experiencing a larger cycle of variability that we hadn't previously charted. And if that was the case, then we would expect to see the star start to brighten up again after it reached its minima or its dimmest point in its known variability cycle. And that's exactly what happened. Over the last month, Betelgeuse has been slowly increasing in brightness. So no supernova right now, though the status quo on supernova for Betelgeuse is it could happen anywhere from within the next 5 seconds to about 1 million years from now. To a human perspective of time, that's a long time. But to a period of time as far as a star goes, that's a blink. So keep your eye on Betelgeuse, because if that star goes supernova, you want to be looking at it. Doesn't pose any risk to us, though the light show we would get would be amazing. You wouldn't need a telescope to observe that supernova, and you wouldn't need nighttime. It would be visible during the daylight sky, and it would be about as bright as the full moon is during the day.
Crazy. So the last thing I wanted to mention was one thing I forgot about on this image was the way that this is scaled is the illuminated moon sections are set up so that the shadow region represents the full shadow of Earth in space at the distance of the moon. So it gives you a way to see how big Earth's shadow is in comparison to the moon. And that's the last thing I had.
When you guys were talking about star hopping before, you talked about binoculars, and someone asked, Don asked, what power binoculars would you recommend?
I usually tell people either go for a 7 magnification with a 50 millimeter objective. So they're usually advertised as 7 by 50. Or you would go with a 10 by 50. My rule of thumb is you want that ratio to be greater than 5. So the big number divided by the little number, you want that to be 5 or more, or else you're losing light if you did the same math for the human eye.
And what those numbers mean, So at 7 by 50, you're talking 7 times magnification with 50 millimeters of aperture. At 10 by 50, you're talking 10 times magnification at 50 millimeters of aperture. And the reason why Derek mentioned these as the sweet spots for viewing space is because you're getting enough magnification to make out details that you wouldn't catch with your naked eye. But at 50 millimeter, you're actually going to collect enough light where you're going to be able to see a lot of other things than just a gray background.
Right.
Nice. Thank you, guys.
Do we have any other questions?
Oh, I would say another thing to consider with binoculars is, much like we discussed with a telescope mount earlier, you want a very good mount. With a pair of binoculars, you're going to need to hold them up. So if you get a very high magnification pair of binoculars that weighs 20 pounds, you might not be able to hold them steady enough to really get a good view. So a smaller, lighter pair might get you a better overall view.
A very valid point.
Yeah, that's a really excellent point that Gavin just made. When you're looking for binoculars, you are going to come across binoculars that are humongous. And you're going to, and I mean, everyone has aperture fever. We've all gone through it. And you're going to say, hey, wait a minute, I can get a 10 by 50, but why don't I get these 20 by 100s? Because they're so much bigger and better. But like Gavin said, they're heavier and the magnification is so much higher that just the jitters in your hands and in your arms become very apparent, and you're not able to resolve your field of view, what you're looking at, because you're shaking too much. So 10 by 50, 7 by 50, not only does it give you the magnification in the aperture to observe space, it also gives you a reasonable amount of stability in just holding them up to your face without introducing too much shaking or wobbling in your view.
One of the coolest things I've ever looked through is Scott's 2x teleconverter. He made these pretty cool binoculars out of 2x camera teleconverters. And he got 2 of them, and he 3D printed a holder for them, so he made them into binoculars. And all it does is basically double your magnification. And it's such a large field of view, but so much magnification that you just feel sucked into whatever you're looking at. And one of the best times to use binoculars is during the middle of the summer when the Milky Way is high and bright in the sky. So you're looking through these things and getting a huge field of view, and they look so small. It's an awesome view. And I think he's trying to look for them right now.
Yeah, I think he is. I just told him, I said, do you have them around? Go try to find them.
Yeah.
Here they are. This is the binoculars that Sean was talking about. I love these. They're really easy to make. I printed the 3D, the shell, 3D printed at the Cranston Public Library in Rhode Island for $1.50. And these lenses used to be quite expensive, but now that they're not really used anymore, you can get them for like 30 bucks. Whenever I give presentations in classrooms in school, before the kids walk into the room, I put them on my face like this. And then when they walk in, they think they're looking at my glasses and are like, oh my God, look at that guy's glasses. But they do give you a fabulous view of the night sky. And it's a really great science project. Now that we're all stuck at home looking for things to do, especially our kids, good idea, right?
Oh, yeah. And the Milky Way is starting to come back in the early morning hours, so it's perfect time.
Oh, yeah.
Also, Charlene wanted to know if you guys had any recommendations for a beginner's star chart specifically for kids to get started, I guess, learning all the constellations and different planets and stars.
So star charting is yeah. These days we feel like, everybody wants to run off and grab the most awesome stargazing app for their phone, and that's cool and all, though there are negatives to it, especially when you're at a site like Frosty Drew Observatory where the sky is just so dark. The backlight in your phone is going to ruin your dark sky adaptation, your ability to see dim objects in the dark, and it's going to kind of steal your view of the night sky. Though we're big supporters of a lot of these fabulous apps, they do make it difficult when you're actually out in the field and you want to actually see the sky. Now, if you want to use an old school star chart to actually look at the sky, there's a couple that we would recommend. So Edmunds Scientifics, their website is called scientificsonline.com. They make all kinds of really excellent introductory scientific tools and devices for people of all ages. And they make a chart called the Edmunds Sky Guide. It's a small magazine type book that will have a star chart in it, but it will also have a lot of introductory material about looking at the sky, about how to look at the sky, about what you're looking at, and how to do basic calculations and measurements when looking at the sky, how to remember where things are. It's a fabulous resource. It's excellent for people who are starting off, and even seasoned physicists will take it out in the field with them because it's so fabulous. If you can get your hands on the Edmunds Scientific's Mag 5 Atlas, so it's no longer in print, you still can find them on eBay or on Amazon Marketplace. That's a fantastic atlas for the sky to start out with. And if you're looking for something that has a few more objects in it that is still easy to use, the Sky and Telescope Pocket Atlas is a fantastic resource that I feel like all the astronomers I run into, they have these in their little bag of tricks.
Thanks, Scott.
Any other questions?
Not right now.
Eric, are you done?
That was the last thing I had, was talking about the shadow.
Okay. So I'm going to start showing some stuff. Cool?
Yeah.
Oh, yeah.
All right. So first up, I'm going to show. So we had someone ask earlier about the owl cluster that Derek was showing. So right here, I have a star charting application called Stellarium open. Stellarium is free. It is open source. You can download it at stellarium.org. And I would recommend it. It's a fantastic application for planning your night out. At Frosty Drew, we use this to control our telescopes. And in your view right here, we have the constellation Cassiopeia. And you'll notice in this little pulsing square, this is where the owl cluster is that Derek was showing you. And this is a good example of how to find it. Now, I'm going to switch over real quick to an image that I captured yesterday of Venus. Now, Venus is in a spectacular phase right now. And as we continue to move through the next couple months, Venus is going to continue to wane more and more. Now, this here is a video of Venus from telescopes I have set up in my yard. My workstation looks absolutely ridiculous right now. I have it outside, and it's part of working in astronomy at home. You got to set up your telescopes. So right now we're looking at Venus. I captured this image of Venus in infrared because it gives me the most stable wavelengths of light. Venus is quite bright, and in the night sky, or in this case, the day sky, you're going to get a lot of distortions from Earth's atmosphere. Now take a look at Venus. When you think about looking at planets in a telescope, you think you're going to look at something that's round. But as we look at objects that are closer to the sun than we are, we see these objects in phases, because the side that's facing the sun, which is the side that we would see, is not fully facing us. So we only see part of the side that's in sunlight, and we see a substantial amount of the side that's in nighttime, though there's nothing to illuminate the night side bright enough for us to actually see it, so it just appears dark to us. That line you see that kind of gives you that crescent view that separates the daytime side from the nighttime side on Venus, that's called the terminator, and it's where sunlight terminates or sunlight ends. And we also consider that the sunset line. Now, Venus is moving around the sun in a counterclockwise motion, just like we are, though Venus's orbital period is about 224 Earth days long. So it's a little bit shorter than our 365-day year. So Venus catches up to us. And as Venus moves around the sun to a position where we can see it, it starts to wane from our point of view, because the side that is in sunlight becomes more and more on a daily basis out of our field of view, or out of our point of view, And what we start seeing is more the nighttime side. And this is the waning crescent stage. Over the next month and a half, 2 months, Venus is going to continue to wane till we get to a point where Venus is just a super thin crescent. And then it arrives at a point in between us and the sun, which we call inferior conjunction. Now, Venus's distance from us tonight is 48,894,797 miles. And that delays our view of Venus by roughly about 5 minutes. So our view of Venus is delayed by 5. You go out in the sky, you look at Venus, you're seeing it about 5 minutes in the past. It's currently in the constellation Taurus, and tonight's phase is 36% waning crescent. Now, here is an image of Venus that's built up from this amount of information right here. That's Sean. But Venus is right here. Now, when we look at Venus, this is a composite image of Venus from all of that information that we were looking at. Sorry, that's my debug window. And this is a composite of the infrared wavelengths of light and the UV wavelengths of light. Now, the reason we do this is because Venus has a significant amount of clouds around it. In fact, it's completely covered in clouds. And to catch a stable image of Venus, we need to capture it in the infrared wavelengths of light. This gives us the most stable image as it results to Earth's atmosphere getting in the way. But by capturing the ultraviolet wavelengths of light, we also can capture some detail in Venus's clouds. When we put these together, we create a false image. I map the infrared wavelengths to the red part of the visible spectrum because it's on the red side of the visible spectrum. And then I map the ultraviolet wavelengths to the blue side of the visible spectrum because it's on the blue side of the visible spectrum. And in this image, you can see Venus's shape, but all the blues you see are details in Venus's clouds. Now, Venus is a terrible place. I mean, it's commonly referred to as Earth's sister, and there was a time where we thought there were dinosaurs, you know, walking around on Venus. You know, the things we learn as time goes by, right? But Venus has something that we call a runaway greenhouse. So when we think about greenhouse gases, greenhouse gases are a good thing. Greenhouse gases are what allows life to continue to evolve and exist on planet Earth. Those greenhouse gases slow down the rate at which heat leaves the Earth, and it keeps it warm here at night. Now, greenhouse gases are a good thing, but the way we're adding greenhouse gases due to human manufacturing processes to the atmosphere are a bad thing, because we're putting the greenhouse gases up to a level where the heat takes too long to escape, and heat gets backed up behind it, and temperatures start getting really hot. Now, among all the greenhouse gases that we experience on Earth, water vapor is a greenhouse gas as well. So when temperatures start to rise, you start having more water in vapor form. Water vapor, being a greenhouse gas, will slow the rate at which heat can leave, increasing the temperature on Earth or in anywhere where we have water vapor, including Venus. And that increase in temperature causes more water to end up in vapor state, which increases temperature, which increases the amount of water in vapor state. This is called a feedback loop. It's logarithmic, and it's unstoppable. This happened on Venus. It got to the point where all the water on Venus ended up in a vapor state. And Venus is now experiencing what we call a runaway greenhouse. And that has put the temperatures at Venus surfaces up to almost 864 degrees Fahrenheit. Think about that, 864 degrees Fahrenheit. That's hot enough to melt lead. And the atmospheric pressure on Venus is hundreds of times the atmospheric pressure on Earth. So if you could visit Venus, it would be like visiting a pressure cooker. Whenever we try to land any kind of satellite or lander on Venus, it lasts for minutes before it fries. And we're working right now on the idea of creating a lander that can last for maybe an hour on Venus to collect enough information for us to really get a good idea of what's happening on Venus's surface from a position of on the surface. So when I was younger, I used to, I wanted to go to space, and I used to have these recurring nightmares that I was going to end up on a Venus mission. And I was like, no, I refuse to go. I will not go to Venus. So we had a question earlier tonight about Comet Atlas. So I have some images of Comet Atlas from recent. This is from March 21st, 2019. And this is Comet Atlas as it was moving through the constellation Camelopardalis. Now, I've been doing a lot of work from home with Brown University, and we're doing a lot of data collection and data processing for the Physics 220 labs that are now happening remotely. A lot of these data sets I'm presenting tonight are products of a collaboration I've been doing with other scientists at Brown University. This image here was processed by me, but it was captured by a fabulous astronomer, telescope maker, and astrophotographer named Robert Horton, who is the astronomy labs manager at Brown University and also the manager of the Alad Observatory in Providence on the Hope and Doyle Street. When you look at this image, you get a fantastic view of Comet Atlas. Now this here is Comet Atlas. It is in the constellation Camelopardalis, which is just north of the constellation Ursa Minor, or the Little Dipper this time of the year. And Camelopardalis is like the giraffe, the spotted camel, or the leopard spotted camel. Now, when you look at this image, there's a lot of things to note. One, you're going to notice that you have the very bright center on Comet Atlas, surrounded by a very green glow. That green glow is called a coma. And coma is a very tenuous or a very thin atmosphere that forms around the comet's nucleus. It forms from the outgassing of volatile or unstable materials inside the comet that are now heating up and reacting to its encounter with the solar wind. Now that solar wind, again, you're talking of a constant outstream of energy from the sun in the form of plasma and charged particles. In this case, they're all magnified. And as the comet starts to encounter this radiation, it starts to outgas. And you'll notice that a small tail forms as well. Now, the tail of a comet always points away from the sun because it's not a product of the comet's motion. It's a product of the comet's interaction with the solar wind. So when the comet reaches perihelion, its closest point to the sun, and it swings around the sun and then starts moving back out, the tail will point away from the sun, and it looks like it's chasing its tail. Now, an important thing to note about Comet Atlas's nucleus is roughly about 3 miles in diameter, though its atmosphere is about half the diameter of the sun. That's how big these atmospheres get. Now, this is an image of Comet Atlas after it had already fractured and started outbursting. We had a substantial increase in outgassing, which made it much brighter, though this is before the large fracture that happened over the past week, which resulted in the comet starting to dim down. Hopefully this week we'll capture additional data on Comet Atlas and we'll be able to show you that dimming. Now I'm going to show you real quick here a video of Comet Atlas that we captured over the last month. And in this video, you'll notice that Comet Atlas, you can see it moving in the sky. Now, I did show this last week, so for those who have already seen this, I apologize. But this is a really fantastic viewpoint of what it looks like when a comet is actually moving in the sky. So, quick, I'm going to load it up. Give me 1 second. That's Sean's lovely face. All right, so here is Comet Atlas's motion in the sky. Now, you'll notice right here is the comet. That little green glow you have in there. And you'll notice you got a little star right to the right of the comet. And you can see that the comet is moving away from the star. This is Comet Atlas over a period of about 1 hour. And this is how much that comet moves in the sky. You'll notice that one of these frames, you see like a streak across the view. That streak is a satellite that's passing through the field. We capture satellites all the time because they're everywhere. Tonight, we have the Starlink constellation, which is a series of satellites that have been launched by SpaceX. That was visible earlier in the night. Now, we've had 5 launches to date of Starlink satellites, and each launch releases a different amount of little satellites into orbit. Over the next 2 weeks, we'll be able to observe at sunset the Starlink constellation. And it's pretty neat to observe. You'll notice that you have a series of satellites that pass overhead, but they're passing at the same distance from each other, and they're all following the same trajectory. It looks like a procession of satellites or moving stars in the sky. You want to check out a site called heavens-above. So heavens-above.com. Put in your location, and it will give you the times that you want to be observing Starlink satellites. We'll also try to post these on our Facebook over the next couple weeks on a daily basis so you can actually get out and see these satellites. So now we're going to move on to another object. And we're going to switch now into objects that are not changing as frequently, some galaxies. So first we're going to start with a group of galaxies known as Bode's group, or the M81 group. Now, this is a group of galaxies that are quite close to us. I'll load it up real quick for you here. Bear with me for 1 second. Every time we switch over, we see Sean, because Sean is such a good-looking chap, isn't he? And he loves doing that, may I add, as well. So this here is an image of the M81 group, also known as Bode's galaxies. On the right-hand side here, you have Messier 81. On the left-hand side here, you have Messier 82. These galaxies reside at a distance of 11.7 million light years distant from us. Now, let me just be clear about something. 11.7 million light years in the galactic scale is close to us, though it's still far enough that our view of these galaxies, when this image was captured about 3 weeks ago, is still 11.7 million years in the past. And if you want to see what these galaxies look like tonight, you have to wait 11.7 million years for that view to get here. Now, this is in the constellation Ursa Major. This grouping of galaxies that these 2 large galaxies are part of is called Bode's group, and Bode's group is comprised of about 34 individual galaxies. Now, Messier 81, this galaxy you have here on the right-hand side, Messier 81 has a diameter of 90,000 light years. So it takes 90,000 years for light to travel from one side of the galaxy to the other side of the galaxy. And that's about 10,000 light years smaller than the Milky Way galaxy where we live, or what we're part of. Messier 81 is the largest galaxy in the local group, and it is considered a grand spiral galaxy. You can notice that the spiral arms are quite visible. And along these spiral arms, you can see a lot of blue color. You also notice that there are a lot of detail in these, and you're looking at a lot of young stars. Messier 81 has a black hole in the center of this galaxy, like most galaxies do. And the black hole in the center of M81 is 70 million solar masses. That means that that black hole has a mass of 70 million suns. That's how big that black hole is. That's how massive that black hole is. Now, Messier 82, that you see over here on the left, Messier 82 is what we call a starburst galaxy. And that means that Messier 82 has recently interacted with another galaxy, which has triggered an intense amount of star formation that happened in this galaxy. So when we think about galaxies, especially galaxies like the Milky Way, or galaxies like Messier 81 over here, these spiral galaxies are very well organized. And along those spiral arms, you have clumps of hydrogen gas, nebula, that is very organized. From a point of view of observation, aesthetically speaking, it looks really awesome. It's beautiful. But from a position of star formation, this is not very efficient. And we end up in a very low point of star formation when we're in the spiral galaxy stage. But when galaxies start to mix, when they start to interact with other galaxies, all of the molecular hydrogen that's organized along these spiral arms starts to become disturbed, and it starts to mix. Some of it mixes with other molecular hydrogen clouds inside the galaxy, other nebulae inside the galaxy, and sometimes they start mixing with nebulae in the galaxy that they're interacting with. And these mixings, they start to trigger a substantial amount of star formation, which is what we're seeing right now in Messier 82 in this galaxy. And that's why we call it a starburst galaxy. This galaxy is undergoing a substantial amount of star formation. Now, it's thought of at this point that Messier 82's interaction with Messier 81 is what's actually triggering this star formation at this point. And the diameter of Messier 82 is about 37,000 light years, so it is quite smaller than Messier 81. Now, at this point, does anybody have any questions about these objects? I see Jessica fervently raising her hand.
Yeah, well, Bo Dugas, he's asking, how far apart are they from each other?
Bo, it is awesome to hear from you. I miss seeing your beautiful face out of the observatory every week. So we're supposed to close up at the observatory at 10 o'clock. But thanks to Bo and his awesome wife, Allie, we're usually stuck there until about 1 o'clock in the morning. Now, I say that with a bit of facetiousness. I love staying out under the stars. And anybody who's interested in hanging out that late with us is awesome. So, Bo, these galaxies are part of a group of galaxies called the Bode's group. So you're talking about an area that's roughly upwards of maybe 30 to 40 million light years in diameter. Now, these galaxies are much closer to each other than that. These galaxies are about 1 to 2 million light years in distance from each other. And though the main part of the galaxy, the galactic disk, may not be directly interacting with each other, the halos of these galaxies are starting to interact. And those halos are transparent. We don't see them readily, but they're transparent bubbles that surround these galaxies. And these halos are starting to interact. So earlier tonight, Derek was talking about the galaxy, the Phantom Galaxy, and that it takes up a little less than an area of the full moon. When you're looking at the Andromeda Galaxy, you're talking about a diameter of 6 full moons in the sky. Though the Andromeda Galaxy's halo takes up almost 100 degrees of our sky, but we don't readily see it. So, any other questions?
Another interesting fact about M82 was that in 2014, it had a supernova that we could see with telescopes visually.
Yeah, so SN 2014J is the supernova that Derek is talking about. And this was a fantastic supernova. It was a type 1A supernova, which is not exactly the type of supernova that we think about when stars die. It's a product of two stars that are in the same star system, so a binary star system. One of the stars dies, and when that star dies, it turns into a white dwarf. And it changes the equilibrium, that balance that these two stars have as they orbit around each other. And the other star may end up passing quite close to the white dwarf, that stellar remnant. If it crosses a region that we call the Roche limit, which is the distance where the gravitational forces of one star can have a detrimental effect on another star, tidally speaking, its tidal forces, then that white dwarf starts to steal a lot of the mass or matter from the other star that's still alive. And that matter starts to collect, we call this accretion, on the surface of the white dwarf. Now, mass plus gravity equals heat, and this is what triggers star formation in the first place. Though in the case of a white dwarf, all of this accreted, all of this gathered matter starts to increase the temperature of the white dwarf. And eventually it reaches a point at which we start fusing a lot of that hydrogen, that stolen matter, to heavier elements like helium. But instead of happening inside the core of that white dwarf, it happens on the surface of the white dwarf. And thermonuclear runaway occurs. It's an intense nuclear reaction that destroys the white dwarf and generally destroys the other star as well. This happens at 1.44 solar masses, which is called the Chandrasekhar limit. And because it happens at that point, we always know how bright they're going to be. They're always the same brightness. For a very brief period of time, about a month, a type 1a supernova will become brighter than everything else in that galaxy. Though because we know exactly how bright it is, we could get a much higher precision in our calculation of distance to that object. And that's why we consider type 1a supernova standard candles. And the reason, or the way we can tell that type 1a supernova is occurring is through something called a light curve, which is where over a period of its brightness, we measure every night how bright it is and we chart it on a graph. And then we get a signature of that supernova's brightness. And a type 1a supernova will have a very specific signature. Once we identify that signature in the light curve, we know we have a type 1a supernova, and then we know we could use that event to measure the distance to that object. In this case, that galaxy.
So it seems like Bo had another question. He said, is M81 big enough to take up M82 at some point?
So that's a fabulous question, Bo. And we miss you, may I add? And I hope to see you guys soon. I'm tempted to break quarantine protocol and come in and visit, but I know that that would be not a good example, right? So Messier 81 is the larger galaxy of the two. And though Messier 81 and Messier 82 both will not survive that interaction as we see them today. So when you're looking at these two galaxies here in the field, you got Messier 81 has a nice spiral shape to it. And Messier 82, it's kind of a mess. When these galaxies start to come together, both of these galaxies are going to become very disturbed. And they're going to become, all of those stars are going to be flung out into the space around those galaxies. And it's going to start to mix. And eventually it's going to look like just a mess of stars, just a mess of matter. Though you're not going to have stellar collisions happening. You're going to have planetary collisions happening. There's a lot of space in between. But what's going to happen is these galaxies are going to slowly start to come back together, and they're going to form a new galaxy. Initially, it will be a starburst galaxy, and then more of an elliptical galaxy. And then eventually you're going to form into what we call a lenticular galaxy, which is where you have the shape of an ellipse, like an elliptical galaxy, but you're starting to come up with a little bit of patterns inside the galaxy that look like the starting of spiral arms, and that's what they are. It's that organization that begins. And eventually, this galaxy may form back into a spiral galaxy. But eventually, once all that molecular hydrogen is used up for star formation, it will end up as an elliptical galaxy, which will just be a series of very old stars and very bright. And we'll see that in the next image that I show. Any other questions before we move on?
Well, we have two more here, Scott. One from Marie, and she said, when was the last supernova seen and recorded in human history?
So we can answer that question in two separate ways. We can answer it in the context of extragalactic supernovae, or supernovae that take place in other galaxies, or we can answer it in context of the galaxy that we live in, the Milky Way galaxy. So as far as the Milky Way galaxy goes, I do believe the last supernova we experienced in the Milky Way was sometime in the 1980s. It was rather dim. It wasn't very visible. And I believe it's cataloged as SN 1984, but I may be wrong. The last really brilliant supernova that we experienced in the Milky Way galaxy was almost 1,000 years ago. And it left behind a supernova remnant known as Messier 1, or the Crab Nebula. And if you look into the sky into the constellation Taurus, I'll actually bring it up real quick for you here on my star charting application. There is a spot in the constellation Taurus that now has no star at it, but at one time, there was a very bright star there. Let me bring it up real quick here. Okay, so let's see if we can get Stellarium to work for us. Or we're gonna...
The Crab Nebula is a rather, or Messier 1 is a rather famous Hubble image of it, and it's just incredible how big the image looks. And then you try and image it, like me or Derek or Scott try and image it, and it's such a tiny object.
Yeah.
One of the other interesting things about it is because it is such a young object, you can actually see differences between the pictures that Hubble takes and the pictures that you take today. There's movement in that object.
Oh, yeah.
It's evolving.
Yeah. And that one was actually recorded in Chinese history, and that's something that, you know, we have that as a human society in our written record because of that.
Right, and at the time they didn't really know what it was. They documented it as being bright light and seeing it through the day and etc. And now here we see it today as a very bright nebula. Does anyone have a picture of Messier 1?
I might. Let's see if I can dig it up. Before Scott gets back.
Yeah, I don't have any particular.
I know it's not particularly good, but it's an image.
I could get the Hubble one up.
That's cheating.
It's a good image.
It's a good image, but
of course it's cheating.
there we go.
Every time I try and image that one, it's just too small for my setup.
It works in my my RC with a long focal length.
So I tried it with that one. I never had good success with my camera. And welcome back, Scott.
Hey guys. So my laptop just exploded again on me. I take a lot of solace and maybe a slight bit of pride that my Linux laptop explodes, but Linux is still amazing. So that's definitely not a political statement. Let me bring this up real quick for you guys here. I'm going to come back a little bit. So, you know, we're in a time of the year right now where we have the sun is slowly moving towards Taurus. So our views are getting a bit.
We were here talking about Crab Nebula while you were gone.
Yeah, we were looking for pictures. I don't have any. I think Derek said he was.
I have one. I got to dig it out though. So
yeah, it's a faint fuzzy in mine. It's not processed. So.
You got it?
Yeah, I got it. Let's see a window. All right. So the little fuzzy blob in the middle there.
That's good though. You can see structure in it.
Yeah. So you can kind of see, you know, that this is like the remnant of that supernova, and what's left behind is the diffuse gas of that explosion expanding. I don't know. You can't really see too much more in here. Maybe a little bit of red along the edges, but other than that, that's about what you would see through a telescope. It wouldn't maybe be that defined, but you would be able to tell that it was lighter than the space behind it. So,
and the one really great thing too about the supernova remnant is that in the center of the supernova remnant is a pulsar, and this is one of the most studied pulsars that we've probably observed. And when a pulsar it's a neutron star. So a neutron star is what remains after a supernova occurs in most cases. What happens is when a supernova happens, it blasts all the outer layers of that star off and just the core is exposed. But the core is so dense, so compact that all of the electrons and protons in that core smush together and form neutrons. And that star is very neutron heavy, that remnant. And that's why it's called a neutron star. So think about a star that's the size of maybe Providence, the city, but it's got the mass of the sun. That's a neutron star. In the case of a pulsar, that neutron star is spinning very quickly. We're talking hundreds to thousands of revolutions per second. on its axis, and it's got a substantial amount of gravity and and a huge magnetic field, and eventually that magnetic field starts to arc out from its poles, and it starts to shoot out a substantial amount of radio light from its polar regions, from the north and south poles. But as that star spins, it also has a wobble in it, and this is called precession. So think of a top spinning really fast on its axis, and it starts to wobble a little bit. As that star wobbles, that precession, it causes those light on the poles to spin around. And if that light crosses over you in the sky, you get a blip in the sky, like a blinking. And it looks very organized. And for a while, we thought it was them aliens. And then after we observed enough of them, we realized that we were looking at another type of stellar remnant, a pulsar.
Now, that's one of the closer pulsars to Earth, correct?
It is. Definitely. I mean, Messier 1, when this supernova occurred, this object was extremely bright in the sky. It was heavily cataloged all over the world. And this resides at about 6,500 light years distant from us. And for probably a good month, this was probably one of the brightest objects in the sky aside from the sun.
Cool.
So
Let me go back to you, Scott.
okay, so I'm going to go back. And this time we're not going to crash the computer, right? Good. That's a good plan.
That's a good plan.
So
Scott, while you're getting this up, maybe you can answer this question too from Ken. He said, what are the sources of Scott's information, or does he just make it up as he goes along?
I am really good at just making it up. So so is this Ken?
Yes.
So Ken, well, so I work in this field, and I spend a significant amount of time every day looking at the sky, reading scientific papers, talking with other astronomers, and laying on the hood of my car looking at space. And when you repeat this stuff enough, it just kind of sticks. So for everyone who's watching tonight, you might be hearing a lot of really great things for your first time, but I've said this stuff so many times at this point that I don't even have to think about it. You know, I got my bottle of whiskey here, and I'm just kind of rattling it off, right? Okay.
Another quick question was, what's your favorite planet to photograph? And this is from Oscar.
Well, I think every single one of us can answer that question, but I'll say it first. My favorite planet to photograph is totally Earth. It's very easy to capture images of. It's here all the time. And even when weather's bad, I can still capture a decent image. John?
Mine, Saturn.
Yeah, I'll second Saturn.
Gavin?
I'll be different and say Jupiter, because you've got those very bright moons around it that do interesting things. It's, particularly in New England, where we've got very poor seeing in the atmosphere, having that nice bright object, it's kind of good to look at.
Yeah, that is cool too.
The other thing,
See, I was waiting for someone to say Pluto and engage the debate about Pluto's planetary status.
well, nobody's going to beat the that New Horizons probe. So
Yeah, right. I mean, what's the point of that, of imaging it after that happened?
right,
Thanks, New Horizons.
all we would do is get more than 10 pixels, and we would beat Hubble.
So, do we have any more questions, Jess?
Well, there's one that's very kind of off topic, and he knows that, but from Bob, he said, this question's off topic, but could you explain if this remote presentation is easier using YouTube Live rather than Zoom?
We're not using Zoom, Bob. We are using Hangouts Meet. And we are streaming it to YouTube Live. Now, we've debated on using a couple different platforms. Next week, we were actually going to try Zoom possibly in our testing. And we've also debated on the possibility of having everybody run broadcast software like we're running on our streaming server and piping into YouTube. It's a learning process. If you have any recommendations for us that you think we should hear, then by all means, please send them to astronomer@frostydrew.org. We would love to hear them.
Yeah, this is one giant experiment for us.
Yeah.
Last
Yes.
week, lost Scott for 10 minutes right at the beginning.
Yep.
Then we ad-libbed it for a while. It was an experience. But we love astronomy. We love reaching out to the public about astronomy, and we wanted to figure out how we could carry it through this very interesting social experiment that coronavirus has us doing.
Yeah, and it has been interesting to say the least, but we are enjoying every minute of it. So the last object we're going to look at tonight is this image here. This is called Markarian's chain. Markarian's chain is a chain of galaxies that is found in the constellation Virgo and is part of what we call the Virgo cluster. Now, the Virgo cluster is part of the Virgo supercluster, and we're part of all of these clusters of galaxies. So let's start with just this image here. Now, Markarian's chain is comprised of different galaxies and different galaxy types. So the first galaxy, this bright one you see right here, this galaxy is called Messier 86, and this is an elliptical galaxy. Just above it over here, we have Messier 84, which is another elliptical galaxy. To the left and the right, on the right over here, we have Messier 44, or I'm sorry, NGC 4461, which is an on-edge galaxy, and NGC 4458, which is another on-edge galaxy. Down here, this galaxy here is very warped. You can see the galactic plane is very thrown off. And this is likely happening due to an interaction with the galaxy that is right next to it. These two galaxies here, the one with the warp, is called NGC 4438 and NGC 4435 right next to it. And these are also commonly referred to as the eyes. As we move down, we have NGC 4473, NGC 4479, NGC 4477, NGC 4459, and then this guy out on the edge over here is NGC 4474. Now, all of these galaxies that form Markarian's chain are very close to each other. Now, I want you to take a look at this image, though. Aside from the image, the galaxies that we've noted, in the background, a lot of these stars that you see are actually galaxies. So take a look over here. Look at all these galaxies in the background here. Galaxies over here. You have galaxies down here. Galaxies out here. All over this image is just loaded with galaxies in the background. And this is kind of an idea of how many galaxies are actually out there in the universe. I mean, there are trillions of galaxies out there. Now, when we talk about the Virgo cluster, which we're part of, the Virgo cluster has a diameter of 15 million light years. And from us to the center of the Virgo cluster is about 54 million light years. The Virgo cluster is made up of about 2,000, up to 2,000 galaxies. The local group, which we're in, is part of this cluster, though the Virgo cluster is part of the much larger Virgo supercluster. The Virgo supercluster has a diameter of 110 million light years. Think about that, 110 million light years. That means at the speed of light, it takes 110 million years for light to cross that cluster once. It has a population of up to 100 galactic groups and galactic clusters. And we're all part of this galactic cluster. This object, Markarian's chain, is perfect for viewing right now in the night sky. As we go into May, we enter what we call galaxy season, and that's because the Virgo supercluster ends up passing right overhead from our location. So these images we looked at tonight, and what we're talking about is a taste of some of the amazing things that we can actually see from Frosty Drew Observatory and from the skies overhead in our area of southern New England. Even though we're closed right now to the public, due to the current situation, we are going to continue to offer these Stargazing Nights events for online. We really want to be hooking up our telescopes and showing you live views. The idea of us sitting around showing you images that we captured earlier in the week or last week or 6 months ago, it's great because it gets us a chance to show off the work we've been doing, but showing you guys the actual live sky, actually what's happening in space, that's what we're all about, is inspiring you guys to step outside, take a look at the sky, and reach for great things. To all the kids that were on tonight, and that may still be on, though it is getting late, it's important to note that if you're between the age of 5 and 21 years old, now 21, you're not really a kid, right? I mean, maybe to us old guys you are, but you guys are all Mars generation. And Mars generation means that in the 2030s, we're going to send the first humans to Mars. We're talking about 10 people likely will be on this mission from countries all over the world. These 10 people, including people from the United States will be on this, are going to be the first humans to ever visit another planet. On that mission, one of those astronauts will be the first one to step off that spacecraft and put their boots on Mars. And that'll be the only human in the history of our species to set foot on another planet for the first time. Those 10 people are walking around on Earth right now. And if you're in between the age of 5 and 21 years old, they're in your age range. They don't know it's them. And it could be you. That's awesome. Now, it doesn't have to be you. I understand that there's a lot of stress and a lot of pressure in that statement, but it can be you. And that's amazing. So if you're having a bad day and you feel like the world's coming down on you, remind yourself that you may be able to walk on Mars one day. You have that opportunity. So as we come to the close of our session tonight, I want to note that thank you for joining us. We are trying our best to bring space to you in the comfort of your homes as you are off physical distancing. Though if you learned anything tonight, if you had a great experience tonight, if you were inspired, or if you just like what we're doing, then please consider donating the Frosty Drew Observatory. You can find our donate link in the description below the live stream tonight. Our moderators have been posting it to the chat tonight, and they will continue to post it until we're over. And it's frostydrew.org/donate. Anything you can donate to us is greatly appreciated. It is because of people like you that we can do the things we love and bring space and the cosmos to everybody. So please consider supporting us as we go through this tough time. And we can't wait to see you guys again out under the stars. Does anybody else have anything to add?
There was a quick question. It said, do we ever look up and see what we think is a star, but it's actually a galaxy? And if so, what are the more famous ones?
You want to take that, Gavin?
This is actually kind of beyond my astronomy knowledge.
I was going to open it with the only galaxy I know that we can see naked eye is the Andromeda Galaxy, other than the Milky Way. The Andromeda Galaxy is in the constellation Andromeda. You can find it by following the larger of the two Cassiopeia Vs, kind of directly down from the larger one. And you'll see a faint fuzzy spot in the sky there. And Scott said it earlier in the evening that galaxy takes up about 6 full moon widths in our sky as far as the light that it presents to us. On a dark night, you can absolutely see that with the unaided eye. And no binoculars, no telescope, no binoculars. The unaided eye, you can see that, and it's pretty cool. And that's about 2.5 million light years away.
And when you see it, look at it with the naked eye, you can really get a perspective on how big that object is.
Any other questions before we wrap it up?
Nope, I think we're good.
All right, guys. So thank you very much for joining us tonight. We love doing this, and we love that you've been hanging out with us. And let's hope for clearer skies next week. We're also going to start adding a live stream during the day as well, where we're going to have the sun on view and we're going to have Venus on view and the moon if it is up. We will be posting details to that this week on our Facebook, which is facebook.com/FrostyDrewOBSY. And you can learn more about what we're doing by visiting our website at frostydrew.org. We love seeing you guys tonight, and we will see you again this week.